Alright, it's Niyaki Osteozone. So today we are going to have the Niyaki chemistry series, and we are going to discuss on chemical energetics and chemical kinetics, also known as reaction kinetics. So we are starting with this one, chemical energetics. So normally for O level we just discuss the surface of chemical energetics, right? So we want to explain what is meant by the endothermicity of a reaction, the exothermicity of a reaction, the enthalpy change, the effect of a catalyst, how to calculate the enthalpy change using the bond energies. That's what we want to understand in this session, right? So for O level we don't explain the enthalpy changes, the enthalpy change of solution, hydration, neutralization, combustion, and etc. We don't normally discuss that for O level. It's for A level chemistry, right? So for O level, we only need to understand the introductory concept. That's all what we need to understand when it comes to chemical energetics, right? So chemical energetics is defined as the study of energy changes during a chemical reaction. So it is the study of energy changes during a chemical reaction. So this one is the definition for chemical energetics, right? So you need to understand that each and every chemical reaction involves the transfer of energy in the form of heat. So let me highlight that one. Each and every reaction involves the transfer of energy, usually in the form of heat, right? So we are having the transfer of energy, right? So from the thermodynamics laws, we understand that energy is neither created nor destroyed, but it's transferred from one form to another, right? So we have key concepts that we need to define, right? So we start with energy. So from the physics point of view, we defined energy as the ability to do work, right? So energy is defined as the ability to do work, right? And then the system. So the system can be defined as the substance or the chemicals reacting, right? So you can say the reacting substances. And then we go on to explain what we call the surrounding. So we define endothermicity or exothermicity with respect to the surrounding, what you call the everything outside the system. Are we together? And then we have the main or the major term when it comes to energetics, which is the enthalpy. So enthalpy is defined as the heat change of a reaction. The heat change or the energy change, heat change of a reaction, right? And then we go on to define the term exothermic and endothermic. So we're having exothermic and then endothermic, right? So a reaction can be either an exothermic reaction or an endothermic reaction. So exothermic reaction is defined as the reaction that releases heat to the surrounding. A reaction, so we define the term surroundings, right? A reaction that releases heat to the surrounding, right? And then it is negative. The sign of exothermic, it is negative, delta H. So this delta means change, right? Change in heat. So it is negative, right? This triangle means we are having a change in heat, delta, right? And then we go on to explain the endothermic reaction. So endothermic reaction is defined as a reaction that absorbs heat from the surroundings. So this one releases, and then this one absorbs, right? So a reaction that absorbs heat from the surroundings. Are we together? So we say this one is negative, so this one is positive. Are we together? So this is what you need to understand. So examples of these reactions, examples of these endothermic and exothermic reactions. So for all level, only just to list the examples, to know the examples, right? So examples for the exothermic reactions, we have the combustion, what we call the enthalpy change of combustion. We have the neutralization, and we also have other metabolic processes, biological processes, the respiration. So respiration is defined as the catabolic breakdown of glucose to produce heat, right, in the form of ATP, adenosine triphosphate, right? And then we go on to the endothermic reactions. So for the endothermic reactions, we have photosynthesis, right? And then we have thermal decomposition of either carbonates, nitrates, and etc., right? Thermal decomposition. And also we have the dissolving of ammonium nitrate. So this is the chemical formula for ammonium nitrate, right? So this is what you need to understand. This is what you need to know. So exothermic reaction is also defined as the bond formation mechanism, and then endothermic is defined also as the bond breaking mechanism, reaction or mechanism, right? So this is what you need to understand. Are we together? So for all level, we want to explain the energy profile diagram. So this is frequently examined, so you need to take note of this one, the energy profile diagram. So we are having this one. So this one is the progress of the reaction, right? And then this is the energy content, right? Energy content. So you need to understand that for exothermic reactions, so let me draw. For exothermic reactions, the products, they have lower energy content compared to the reactants. These are the product, and then these are the reactants. The products, they are at lower energy level. So this is the energy, the vertical axis, and then this is the progression of the reaction, the horizontal axis. So the products, they are at lower energy level compared to these reactants. Why? Because energy has been lost to the environment. So we said exothermic energy is being released to the surroundings, right? That's why the products, they have lower energy content compared to the reactants. So this is the starting point for all the exothermic reactions. So in your examination, you're going to be given a chemical reaction. So what you need to take note of is this enthalpy change, the sign here. So if you're having a negative here, we are going to have this energy profile. The energy profile is for all, it is universal for all the exothermic reactions. So once you master this one, you're good to go, right? So you only need to change the products and then the reactants, right? That's where you're only going to change, but the shape of the graph is the same, the labels of the graph is the same, right? So this is what we call the energy profile. So for the energy profile, you need also to label kinetic, the activation energy, right? So this is the activation energy, right? So activation energy originates from the reactants to this what we call the transition state, right? And then we have the enthalpy change. So enthalpy change also originates from the reactants going to the direction where we are having the products. So it is pointing downwards because we are having the products downwards. So the direction of these arrows is very, very important. So you understand later on when you are doing A-level chemistry, the importance of the direction of this arrow. So when an arrow is pointing upwards, it simply means to say the reaction is endothermic. And then when an arrow is pointing downward, the overall reaction is exothermic. So we're going to have what we call the Bonner-Haber cycle for the A-level chemistry. That's where you're going to understand this. So when arrow pointing upward, it is endothermic. endothermic, and then downward it is exothermic reaction, right? So we said this one is the activation energy, and then this one is the enthalpy change, right? So activation energy is defined as the minimum amount of energy required to start a chemical reaction. It is the minimum. So we're going to discuss much when we are doing a reaction kinetics. As for now, we need just to appreciate, right? So this is the minimum amount of energy required to start a chemical reaction. So this is what you need to know. This is how you draw the energy profile. You label this one, the enthalpy change, the activation, the products, the reactants. This is what you need to know for all the exothermic reaction. The arrow points downward, and then here the arrow points upwards. As simple as that, right? And to draw the graph or the energy profile for the endothermic reactions, right? For the endothermic reactions. So for the endothermic reactions, the energy profile, the energy content for the reactants is lower than that one of the products. The products are at a higher energy level compared to the reactants. Why? Because the energy is being absorbed, right? So the products are at a higher energy level. So this is the starting point. So for the activation energy, we said activation energy originates from the reactants to this transition state. So we are going to have our enthalpy change. And then we said for our activation energy, and then we said for the enthalpy change, it also originates from the reactants going to the direction where we are having the products. So here the products are on the top. So we are going to have the arrow pointing upwards. So here is our enthalpy change, right? So this is what you need to understand. You should be able to label the enthalpy change, the activation energy, the products, and the reactants. So this is the progression for the reaction, and then this one is for the energy content. So this is how you label the energy profile diagrams, right? For all the endothermic reaction, all the endothermic, and then for all the exothermic reactions, right? So we also have another concept which we need to dissect. We have what are called the bond energies. The bond energies, right? So we have another concept which we need to dissect, which is called bond energies, right? So bond energy is defined as the energy required to break one more of a covalent bond in gaseous phase. To break one more of a covalent bond in gaseous phase. So we only need to underline the term gaseous phase of a covalent bond, right? We don't apply the bond energies in the solid or in the liquid phase. We only apply them in the gaseous phase, right? So let us say we are given the reaction for the chlorination of methane. So we're going to have CH4 here plus chlorine to give us chloromethane plus hydrogen chloride, right? So this is the chlorination. It's called the free radical substitution in organic chemistry, right? So we're going to use the bond energies, right? So here we're having, this is the displayed formula, and then here the displayed formula, and then here to give this one, and then here we're given this one. So you need to know, so in the examination you'll be given the bond energies of the carbon to hydrogen bond, and then chlorine to chlorine bond, and then chlorine to carbon bond, and then hydrogen to chlorine bond, right? So the carbon to hydrogen bond, it is equal to 412 kilojoules per mole, and then the chlorine to chlorine bond, it is equal to 242 kilojoules per mole, and then the chlorine to carbon bond, it is approximately equal to 338 kilojoules per mole, and then the hydrogen to chlorine bond is equal to 431 kilojoules per mole. So don't worry about these bond energies, you'll be given in the examination. So what I want to teach you is how to use the formula, the calculation of enthalpy change using the bond energies, right? So for the bond energies, we are going to use this formula which says enthalpy change is equal to the energy. So it is the summation, the total energy of bonds in reactants minus the summation of energy of bonds in products. So this is the formula you are going to use. These are the reactants, right? And then these are the products. So we are simply going to add, so the formula says reactants minus products. So we are simply going to add the total energy content within these bonds and then the total energy within these bonds, and then we subtract the source summation here from the summation we are going to have here, right? So this is how you need to apply the formula. So at times it can be further simplified as the total energy to break the bonds in the reactants minus the total energy to make the bonds in the product, right? So it is the total energy required for bond breaking minus the total energy for bond formation, right? So this is bond breaking, right, minus bond formation, right? So it's easier for you to understand it in the term of reactants minus products, right? So we're going to have so let us use this one as the examples. So we have methane with CH. So it's C, you see here, and then H there, right? CH. So how many CH bonds do we have? Carbon to hydrogen bonds. We have this 1, 2, 3, and then 4. And then each carbon to hydrogen bond is equal to 412 kilojoules per mole. So we're going to say 4 multiplied by 412. And then chlorine to chlorine bonds, how many do we have? We have 1. And then it's equal to 242. Right? So this is the energy content for the reactants. We go straight to our calculator, right? And then from the calculator, it's 412 by 4. And then we are going to add 242 to have 1890, right? And then for the products, you're going to have 1, 2, 3, right? So it's 3 by 4, 1, 2, and then we have this carbon to chlorine bond. So carbon to chlorine, we say this 338, and then we have this hydrogen to chlorine bond is 431 plus 431, right? So we're going to say 412 multiplied by 3 plus 338 plus 431, and we are going to have 205, right? And then the formula says reactants minus products. So these are the reactants, these are the products. So it's 190 minus the products 205, right? And we are going to have negative 115 kilojoules per mole, right? So when you are having a negative number, we said negative is equal to exothermic reaction, right? So this one is an exothermic reaction, as simple as that. Are we together? So this is how you are going to use the bond energies. First you need to write the equation, and then we're going to apply this only for the elements in the gaseous phase, right? So the definition requires only elements in the gaseous phase, right? So we are now moving into the reaction kinetics, right? So reaction kinetics, right? So we must explain and try to understand what is meant by the term reaction kinetics, right? So reaction kinetics, it is the study of how fast a chemical reaction occurs, and also the factors that affect the rate of a reaction. So we are talking about the factors that affect the rate of a reaction. So what do we mean by the term the rate of a reaction? The time taken for the reactants to be converted into products. That's what we are talking about, right? So we want to understand the effects or the factors which governs the rate of a reaction, right? So for the reaction, we're going to have the decrement in the concentration of the reactants and the increment in the concentration of the products. So we're going to explain this when we are doing equilibria. That's where we are going to explain much of this, right? So we can define the rate of a reaction by saying that it is the change in concentration of our reactants and products per unit time, right? So whenever you are talking about rate, always remember that we are talking about time. So we have other terms which we need to define, like activation energy. So activation energy is defined as the minimum amount of energy required to start a chemical reaction. The minimum energy required to start a chemical reaction. So we have what you call the catalyst, right? So these are the factors which affect the rate of a reaction, right? So for the factors affecting the rate of a reaction, for the factors we have temperature, and then we have concentration, and then we have the surface area, and we have the pressure. So pressure affects the gases, right? Not the solids and the liquids. It won't affect the gases. And then we also have the nature of the reactants. So ionic compounds, ionic reactions, they occur at a faster rate compared to covalent reactions. And lastly, we have this one, the catalyst. So we're going to explain the catalyst later. As for now, we want to explain these factors one by one. So we have what we call the collision theory. The collision theory. So the collision theory states that for a reaction to occur, the particles must collide, right? So for a reaction to occur, the particles, they must collide. So they must collide in the correct orientation with sufficient energy to overcome the activation energy. They must collide in the correct orientation with sufficient amount of energy to overcome activation energy. So we defined activation energy as the minimum of amount of energy required to start a chemical reaction. So the particles, they must collide with these properties: correct orientation and the minimum amount of energy to overcome activation energy, right? So if you are having particles colliding with energy less than the activation energy, or colliding in the wrong orientation, we are not going to have a chemical reaction. So we can predict the feasibility of a reaction using the reaction kinetics or using the chemical energetics. Are we together? So we want to explain the factors affecting the rate of a reaction using a collision theory, right? So the speed of a reaction depends on the number of the collisions, right? Depends on the number of the collisions. So if you are having a larger number of the collisions, you can say that the reaction is going to be faster, right? So the reaction is faster when we are having greater number of effective collisions, not just collisions, they must be effective collisions, right? So we want to explain each of these factors. Temperature, right? So we are starting with temperature. Are we together? So for temperature, we are saying that increase in the temperature will result in the increment in the molecular kinetic energy of the particle, right? So increase in temperature will result in the increase in the particle's energy, what we call the molecular kinetic energy, right? So this will result, so kinetic energy is defined as the moving energy from the physics point of view, right? So the particles are going to move faster and they are going to collide more frequently, right? So they are going to move faster and we are going to have an increment in the collisions, right? Collide more frequently. And also we are going to have an increment in the molecular energy of the particle, which is able to overcome activation energy, right? So we have what we call that Boltzmann distribution curve. So for O level, we don't normally want to explain that distribution curve, a Boltzmann distribution curve, but we want to just for you to appreciate that increase in temperature, the particles are going to have increased kinetic energy and also increased molecular energy to overcome activation energy. Are we together? So this is what you need to understand. So with more effective collisions, we're going to have an increased rate of reaction. So you need to also to take note on that one. The more effective collisions we are going to have a faster reaction, right? So in other words, we're saying that increase in temperature is directly proportional to the rate. Temperature is directly proportional to the rate. If I have an increase in temperature, you're going to have an increase in the rate. If you're going to have a decrement in the temperature, you're going also to have a decrement in the rate of the reaction, right? And also we want to explain this using the reaction between calcium carbonate limestone plus hydrochloric acid to give calcium chloride plus water plus carbon dioxide. So this reaction you can be required to measure the volume of carbon dioxide produced at different conditions. If you are to assess the effect of temperature, we're going to carry the reaction at 15 degrees Celsius and also at 35 degrees Celsius. So at 15 degrees Celsius, the reaction is going to be slower, and then at 35 is going to be faster, right? So you can plot the graph, right? So here's the volume of carbon dioxide produced. This one is the temperature, right? This one is the temperature. And then for the vertical axis, we say it is volume of carbon dioxide. So you can see that the volume of carbon dioxide, the graph is going to be steep when using the faster reaction. I mean, at 35 degrees Celsius. And then for the one at 15 degrees Celsius, the reaction is going to be slow. So they are going to meet. So don't mind my drawings. They are going to meet here. Why? Because we are using the same conditions. That's why we are going to have a straight line here. They are going to produce equal volume of carbon dioxide, but at different rate. This one is faster, and then this one is slower, right? And then we go on to explain the effect of concentration. The effect of concentration. So for concentration, the particles in higher concentration, they are going to result in the increment in the frequency of effective collision, right? So we're going to have increased frequency of effective. They are not just collision, they are effective collisions, because we said not all collisions will result in a chemical reaction. Only the particles colliding with sufficient energy and correct orientation, they are going to have a chemical reaction, right? And then we're going to have more particles. So higher concentration simply means that we are going to have more particles per given volume, right? More particles per given volume, right? and then we're going to have the increased some more collisions will lead to more successful collisions per unit time. Are we together? Right? And then this will simply mean that we're going to have an increased rate of a reaction. And then we go on to explain, so we can for this we can be told that we're having hydrochloric acid with the 1 mole per cubic decimeter the concentration, and then this one 3 moles per cubic decimeter concentration. So the one with the higher concentration is going to be faster, so this one is going to be faster, and this one is going to be slower. You see that? So the faster one, so this is the faster reaction, right? And then this one is the slower reaction. Are you together? And then here we're going to have concentration on this horizontal axis. We're going to have concentration. As simple as that. And then we go on to explain the effect of surface area. So for surface area, we are using large lumps and powdered calcium carbonate. So the one where we are having large lumps is going to be slow. This one is going to be slow, and then this one is going to be fast. So we are having, these are the lumps, right? These are the lumps. So the effect of hydrochloric acid is going to be slow here, and then these are the powdered ones. So these the calcium carbonate has been crushed, and then we're having the powdered one. So the effect of hydrochloric acid much faster on this one. Why? Because the calcium carbonate has been more exposed, right? So it will result in more frequent collisions, right? So you're having more particles exposed in the reaction, thereby more effective collisions, thus rate will increase. So only here you can only see that the particles on the surfaces, these particles on the outer surfaces, they are the only one which are in contact with the hydrochloric acid. The inner surfaces, they are not in contact with the hydrochloric acid, right? The same scenario here, but in the powdered one, the particles has been crushed. All the particles are in contact with hydrochloric acid, right? So the one with the lumps is going to be slow. So this one is the one with lumps, and then this one is the one with powdered. Simple as that. And then we go on to explain the effect of pressure. So the effect of pressure, we normally discuss pressure for the gases. We only discuss pressure for the gases. So increase in pressure results in the compression of the gas particles into a smaller volume, right? So increase in pressure will result in the compressing of the gas particles into a smaller volume, right? So this will increase the concentration of the particles, thereby we are going to have more effective collisions, right? So this will increase concentration, and we are going to explain the effect of concentration like what we did. Increase in concentration will result in the increase in the number of effective collisions, thereby we are going to have increment in the rate, right? It's simple as that. And then I will go on to explain the effect of a catalyst. So a catalyst is defined as a chemical substance which increases the rate of a chemical reaction by providing an alternative route with lower activation energy. a catalyst doesn't lower activation energy. It doesn't lower activation energy. You need to take note of that one, right? It doesn't lower activation energy, but it provides an alternative route with lower activation energy. So we have two types of catalysis. We have heterogeneous catalysis and homogeneous catalysis. So we're going to explain much when we are doing A-level chemistry. As for now, just appreciate that a catalyst increases the rate of a chemical reaction without itself being changed by the reaction. So a catalyst is not changed after the reaction, right? Not changed after the reaction. And then it doesn't lower activation energy, but for O-level times, the exams can say that it's lower activation energy. You need to take it in that way. But when you are doing A-level chemistry, that's where you are going to understand that a catalyst doesn't lower activation energy. It provides an alternative route with lower activation energy. Right? Let us say we're having this reaction mechanism, A plus B producing C plus D. And then the reaction is proceeding in this direction. So a catalyst will be here. So this will react in this direction. And then the products are going to be formed in this direction. We have avoided this straight route. So this is the alternative route with lower activation energy. Are we together? So this is what you need to understand for a catalyst. So at times a catalyst can be introduced in energetics, right? So when a reaction is catalyzed, we're going to use lower activation energy. So this is the activation energy, right? This is the activation energy. So here we have a reduced activation energy. So this one is the catalyzed reaction, and this one is the uncatalyzed reaction, the one without a catalyst, right? And then we can also apply on this endothermic reaction, right? So this one is the uncatalyzed, and then this one with the lower activation energy is the catalyzed, right? So I think you are good to go for all your examinations.